Okay, here we're going to look at the practice test for number 11 for Unit 11, Properties of Gases. So, according to the kinetic molecular theory, which observation below is not correctly explained? Alrighty, well, remember we talked about the kinetic molecular theory, the idea that, pressure is equal to the particles bouncing into the walls of the container, temperature is the speed of the particles, things like that. So decreased volume of gas, okay, results in increased pressure of a gas. So that makes sense. When the volume goes down, the pressure goes up. Okay, explanation. More particles in an area have more collisions with the walls. Okay, if you decrease the size of the container, then those particles, okay, are in a smaller area, and so they're going to bump into the walls more often. So yeah, this is a good explanation. That's a good explanation there. Look at B. So that's not the answer. B, increased temperature of a gas results in increased gas volume. So they move faster and faster, and they're going to bump into the walls of the container. So particles move faster, colliding more often and harder with the walls. That's a good answer. Okay, that's why, like in a balloon, if they move faster and faster, then they're going to collide in the walls of the container, and that's going to push the walls back more. So that's going to increase the volume. So that makes sense. So that's not the answer. Increased temperature of gas results in increased gas pressure. So if the temperature goes up, the pressure goes up. Okay, particles move faster, that's the temperature, colliding more often and harder with the walls, that's the pressure. So that's a good answer as well. So all three of these are pretty good answers, and good explanations. So the answer must be D. All three of these are correct. And that's answer was question 1. That's a lot of reading. So again, with the kinetic molecular theory, keep in mind the idea that temperature is how fast the particles are moving, and pressure has to do with collisions with the walls of the container. That's misspelled. No, it isn't. And one little thing that came up, is that when they are, when you can move faster, two things happen. They move they move faster, and they hit harder. So they're going to hit more often with the walls of the container, and they're going to hit harder. So it has kind of like a double effect. Number 2, which of these is not correct under kinetic molecular theory? Gas molecules are constantly moving. No, that's fine. Remember, we're looking for things that are not correct, so that's a good one. The pressure is related to the number of collisions the molecules make with the walls of the container. That's good, so that's not the answer. The volume of gas molecules themselves is negligible compared with the volume of the container. That's true. We're saying that the particles, are like little points. They don't have any volume. And there are attractive intermolecular forces such as London dispersion forces between the gas molecules. Okay, we're saying that is not true in our kinetic molecular theory of ideal gases. We're saying that the particles, don't have any attractions. You can squeeze them closer and closer, and they will never stick together. So D is the answer. That's not part of our kinetic molecular theory. Okay, number 3. Here's a graph. Shows a relationship between which sets of gas properties. Okay, well, you should look at that and say, okay, that is a direct relationship. So we're saying that when X goes up, Y also goes up. Okay, not like P and V. Remember, P and V looks something like this. Okay, so could it be pressure and volume? No. That's, one goes up, one goes down. Volume and temperature, that could be it. Pressure and temperature, that could be it. They're both in a situation when the temperature goes up, the pressure goes up. When the temperature goes up, the volume goes up. So we're looking for an answer 2 and 3 only. That looks like answer C. Okay, number 4. A balloon is inflated with oxygen gas at 15 degrees to a volume of 1.2 liters. If the temperature is increased to 25 degrees at constant pressure, then, okay, so what happens? So we're saying we have a temperature and we have a volume. Now we get to a higher temperature. So what's going to happen to the pressure? Not pressure. What's going to happen to the volume? Okay, so a balloon's inflated, and it warmed it up. The number of moles of oxygen decreases. No, that stays constant. The number of moles increases. No, it stays constant. It has to do with the volume. So if we increase the temperature from 15 to 25, then the volume is going to get larger. If you heat up a balloon, it's going to get bigger. So it's just the volume of the balloon increases. Answer D. Number 5, a sample of gas originally at 12 degrees is heated, so its total kinetic energy doubles. What is the new temperature of the sample? Okay, well, if we've doubled the kinetic energy, that means we've doubled the temperature. So you might say, okay, well, if I've got 25 degrees Celsius, if I double that, that's 24 degrees Celsius, but that is wrong, okay? What we have to do is say, no, we have to double it when it's in Kelvin. So we're going to add 273, okay, when we add 273, that gets us, what, 285. Now that's 285 Kelvin. Now we're going to double 285 Kelvin, okay, so what's that going to be? And what I get from that, that's 570 Kelvin. So if that were an answer, that would be good. And there's 570, but that's Celsius, so that's not the right answer. So now we're going to do is go back to Celsius. We're going to subtract 273, so minus 273, and get 297 degrees Celsius. So that's my answer right there. Okay, so watch what just happened. What we had to do is take our number, we had to add 273 to get it to Kelvin, and then we can double the answer. And then once we double the answer, we subtract 273 to get back to the final answer. So take your number, add 273, then double it, then subtract 273. And 297 is the answer. Number 6. A cylinder containing CO2 gas has a piston that can move up and down freely. That means we can change the volume. If the volume of the piston is increased from 1.1 liters to 1.3 liters at constant temperature, which of the following is true? Okay, so we have some gas particles inside here, and what we're going to do is we're going to increase the volume, so we spread those particles out a little bit, and we're not changing the temperature. So the gas molecules hit the walls less frequently. I would say that is definitely true, because they have farther to go. They have to move farther, because the container is bigger, so they're not going to hit quite as often. And that means the pressure is going to go down. So answer A, I think, is good. Let's double check the other answers. The gas molecules hit the walls more frequently. Okay, no, they're definitely not, because it's a bigger container. The gas molecules move more rapidly, move more slowly. No, that has to do with its temperature, and the temperature stays constant. Okay, so it's answer A. Number 7. A rigid cylinder contains 0.6 moles of xenon gas at 50 degrees. If the temperature is lowered to 20 degrees, which of the following is also decreased? So we're saying the temperature is going down. So what's going to go down? Is the pressure of the sample going to go down? Yes. Okay, we know that. The slow down the particles. The average speed at which the molecules travel? Yes. Okay, because that's temperature is the speed of the particles. The number of collisions the gas wall containers make with the walls of the container? Yes. If they're moving more slowly, they're not going to hit quite as often and not as hard. So all three of those are true. 1, 2, and 3. Answer 7. Okay, number 8. A pressure of 745 mmHgs corresponds to how many atmospheres? Okay, that's a good one. So 745 mmHgs. Then we know we need a conversion, and we have memorized that there's 760 mmHgs for every 1 atmosphere. So 745 divided by 760, we need an answer a little bit less than 1. So certainly we can knock those off. In fact, we can knock all those off. We know the answer must be B, even without calculating. Okay, standard temperature and pressure. Okay, that's just a memory thing. Okay, 1 atmosphere, that sounds good. 273 Celsius, that's wrong. 1 millimeter, no, that's wrong. 760 atmospheres, no, that's wrong. 760 mmHgs, 273 Kelvin, that's the answer right there. So just which one has the right numbers. A gas at 750 with a volume of 2 liters is allowed to change its volume at constant temperature until the pressure is 600 mmHgs. What's the new volume? Okay, so what do we have? We have a pressure, okay, and we have a volume. We got a new pressure. What's the new volume? So this is a P1 V1 equals P2 V2 problem. And our pressure is 750 millimeters of mercury times 2 liters is equal to 600 millimeters of mercury times X. Making some shortcuts here so I can fit it in. So X is going to be 750 times 2 divided by 600. So my answer is going to be larger than 2, which makes sense because if I reduce the pressure on a gas, it'll allow it to expand a little bit. So I'm going to get an answer that's bigger than 2. So I can knock off that one for sure. And I certainly don't think it's going to be 15 or 27. Okay, it's just going to be a little bit larger than 2. So I'm almost sure the answer is B without calculating. But I'm going to do it real quick. So 750 times 2 divided by 600 comes out to be 2.5. So that's the answer, B. 11. A sample of gas occupies 324 milliliters, that's a volume. At 40 degrees, we're going to immediately change that to 313 Kelvin. Okay. What volume will the gas occupy at 20 degrees, which would be 293 Kelvin? We add 273 to each of these numbers. There's no change in pressure. So this is a volume and two temperatures. So this is V1 over T1 equals V2 over T2. And what we're saying is 324 milliliters is to 313 Kelvin, as X is to 293 Kelvin. And we can see our temperature is going down a little bit, so the volume is going to be a little bit less than 324. So that's way too low. Okay, that's too big, and that's way too big. I bet the answer is 303. Okay, I'm going to double check my math real quick. 324 times 293 divided by 313. I did it wrong. 324 times 293 divided by 313, 303. Okay, there it is. That's the right answer. Okay, 12. What would be the pressure of a gas originally at 101.3 kPa if the temperature is lowered from 95 to 85? Okay, it's a little tight in here, but I need to change those to Kelvin. So 85 plus 273 is 358. And so this would be 368 Kelvin. So I've got a pressure and I've got two temperatures. So the idea is P1 over T1 is equal to P2 over T2. What would be the pressure of a gas originally at 101.3 kPa if the temperature is lowered? Okay, so we're saying that 101.3 kPa is to, the answers here are all in millimeters of mercury. So when I start here, I don't want to use my 101.3. I know that that is the same as 760. So I'm going to go back here and say 760 mmHgs is to 368 Kelvin, as X is to 358 Kelvin. Now it goes down just a little bit, so I want a number that's just a little bit smaller than 760. So that's too big, and that's probably way too small. So those two are almost identical, so we just have to calculate it out. So this is 760 times 358 divided by 368, and I get 739. Answer C. Okay, so I'm just cross multiplying here. I'm just doing it in my calculator. Okay, 13. A gas at 25 degrees, we're going to change that to 298 Kelvin, and 680 mmHgs occupies 345 milliliters. What's the volume at STP? Okay, so this is a P1, V1, T1, and P2, V2, T2 kind of a problem. Okay, what is the volume at STP? Okay, STP, then the P in STP is going to be 760 mmHgs, because the other pressure we're using, 680, is in millimeters of mercury. And the temperature is 273 Kelvin, that's standard, and the other one was 298 Kelvin. And the volume they had before was 345 milliliters. And milliliters is fine in this, as long as, our answer is going to come out to be milliliters. So now we just have all these numbers, we've got to plug and chug. So we're going to say P1 V1 over T1 equals P2 V2 over T2. And so what do I have? 680 times 345 all over 298 is equal to 760 times x over 273. Okay, now I'm going to cross multiply, and I'm going to do it down here where I have some room. So 680 times 345. So then my two top numbers here, and I'm going to use that bottom number down there, 273, is equal to 298 times 760 times x. So to solve for x, I'm going to divide both sides by 298 and divide by 760. Okay, so that's out of there. So x is equal to, I'm going to calculate. And when I do all this, 680 times 345 times 273 divided by 298 divided by 760, I get 282.787. 282, that makes 283 right there. That's my answer, 13. Okay, now we have our free response. A sample of chlorine is placed in a cylinder with a piston that is allowed to move freely. The sample originally has a pressure of 85 kilopascal and a temperature of 12, which I'm going to change that to what, 273, 283, 285 Kelvin, and a volume of 0.6 liters. Okay, I refer to these initial conditions for each part of this problem. Okay, so we're going to come back to these numbers several times. So I have a temperature equal to this. Okay, I've got a volume equal to this, and I've got a pressure equal here, to 85. Okay, find the pressure of the sample if the temperature is raised to 30 while the volume is fixed. Okay, so temperature, I got a new temperature. Now 30 degrees, I got to change that to Kelvin. So that would be to 303 Kelvin and 273. So find the pressure. Okay, so this is P1 over T1 equals P2 over T2. And to help me organize, I'm going to write my variables over here, P1, T1, P2, T2, because this is the kind of place where I get things all goofed up. So I'm starting off with 85 kilopascals. My first temperature is 285 Kelvin. My new temperature is 303 Kelvin. Pretty messy. So I'm looking for my new pressure. Find the pressure. So my number here is 85 over 285 equals x over 303. And x equals, I get 90.368, so I can say 90.4. And my units are going to match my original units. So I just did a cross multiply. So 85 times 303 equals 285 times x. So 85 times 303 divided by 285, that gave me 90.4. Okay, if the temperature is held at 12 degrees, okay, now that was my original temperature right there. What is the pressure if the volume is allowed to increase to 1.2? So my volume was 0.6. So let's change here. So now we're talking about the temperature is held constant, so we don't care about that. What's the pressure if the volume is changed? So we're talking about P1 times V1 equals P2 times V2. And again, I'll use the area over here, P1, V1, P2, V2. So my original pressure was 85 kilopascals. And the correct, what is the pressure? So I'm looking for P2. My volume originally was 0.6 liters, and now it's 1.2 liters. Okay, so my volume has doubled. My pressure is going to be half. The answer is going to be half of 85, so it's going to be 42.5. But let's show the work. So I'm going to change colors here. So it's 85 kilopascals. Okay, times the volume of 0.60 liters is equal to x times 1.2 liters. And so to get x by itself, I divide both sides by 1.2. And liters drops out. So 0.6 over 1.2, that's half. Half of 85 is 42.5 kilopascals. Okay? Find the volume of the gas if the conditions were adjusted to STP. Okay, we have some room down here. Let's do it down here. So let's get a new color. P1, V1, T1, and we have P2, V2, T2. Okay, and the question here is what would the volume be at STP? So we're looking for that volume. We know the temperature is 273 Kelvin, that's STP. The pressure, because we're working in kilopascals, the pressure is 101.3 kilopascals. Now we have to go back and get our original conditions here. Okay, so originally the volume was 0.6 liters. Okay, the pressure was 85 kilopascals. And the temperature was, what did we say that was? 285 Kelvin. Okay, so all we have to do here, this is P1, V1 over T1 equals P2, V2 over T2. Okay, we're going to substitute in our values. So 85, I'm going to leave off my units to save space, times 0.6 over 285 is equal to 101.3 times x over 273. So solving, okay, I'm going to cross multiply this, this, and this. So 85 times 0.6 times 273 is equal to that, and that. 285 times 101.3 times x. So to get x by itself, divide both sides by 285 and 101.3. That crosses out. So x equals, I'm going to multiply 85 times 0.6 times 273 divided by 285 divided by 101.3. And when I do that on my calculator, I get 0.482256. Okay, so that's good. And this is my volume, so this is in liters, because that's my other number was in liters to start with. So since this was liters, this answer is liters, and that's that answer. Okay, just one more. Okay, a 0.5 and 0.8 liter plastic containers filled with SO2 gas at a pressure of 500 torr, 30 degrees Celsius. We're going to change that to 303 Kelvin before we forget. Calculate the pressure in ATMs. So the first thing all we want to do is we want to just change our pressure. So we have 500 torr, and we know that there are 760 torrs in 1 atmosphere. So 500 over 760, that's going to be smaller than 1. And I get 0.65789. I'm going to say 658 atmospheres. So that'll be my first answer. My next thing here is calculate the temperature in Kelvin. Okay, that's easy. Oh, we just did. Okay, so just show our work here. 30 degrees Celsius plus 273. Okay, gives us 303 Kelvin. We just got 2 points. That's good. Okay, calculate the number of moles of SO2 in this sample. Well, if we're seeing moles, the only problem thing we have, and it has moles, is PV equals nRT. Okay, so let's get our variables here. So I'm going to use some space over here. P, V, N, R, and T. Okay, and we know R is 0.0821 liters atmospheres per mole Kelvin. Okay, I'm looking for a number of moles. What do I have? I know my temperature is 303 Kelvin. I know that my pressure is 0.658 atmospheres, and the volume of the container 0.8 liters. So PV equals nRT. So N is equal to PV over RT. Let's substitute. Okay, pressure 0.658 atmospheres times 0.8 liters divided by 0.0821 liter atmospheres per mole Kelvin, and 303 Kelvin. Oops. And that comes out to be, okay, I get 0.02116. So I'm going to call that 0.021, with you 1/6 would round up to 2. And we're talking about moles. And that's my answer right here. Okay, so the last part here is find the mass of this gas sample. Okay, this is an old problem. So if I have 0.0212 moles, and we're talking about SO2 gas, SO2 gas. So that's moles of SO2. For every 1 mole of SO2, okay, did they give us the molar mass? Nope. Okay, so sulfur, we got to look up sulfur, and we got 2 oxygens. I know oxygens weigh 16, so 2 of them is 32.00. Okay, sulfur weighs a little bit more, it's 32.07. So this whole thing is going to be 64.07 grams of SO2. So I'm going to multiply my answer times 64.07, and I get an answer of 1.355766. Okay, grams. I'm going to round that off to 1.36 grams of SO2. Okay, and it looks like it says find the density of this sample of gas. Okay, well, we have to remember way back that density is equal to mass over volume, dmV. So the mass of this sample is 1.36 grams, and the volume back here was 0.8 liters. And so divide 0.8. Okay, so I get 1.69 grams per liter. And that's what I get as a density. Okay, the last one's here. Magnesium, oh, this is our lab. Okay, magnesium reacts with hydrochloric acid to come following equation. In a roll of magnesium ribbon, a 1 meter piece has a mass of 1.22 grams. Find the moles of H2 that are produced when 3.2 centimeter strip reacts. Okay, so we have a 3.2 centimeter strip of magnesium. We know that 100 centimeters is 1 meter of anything, and that a meter of magnesium weighs 1.22 grams, that's grams of magnesium. Using the periodic table, we know it's 24.3 grams of magnesium for 1 mole of magnesium, and we're trying to find moles of hydrogen. So from our balanced equation, that 1 mole of magnesium is 1 mole of hydrogen gas. So our final answer is, okay, 0.0016. I have 160658, so I'm going to call that 161 moles. So there's that line equation. Okay, the air pressure in the laboratory is 745 millimeters of mercury, and the temperature is 21. If the vapor pressure of water is 21, at 21 degrees is 18.6 mmHgs, find the pressure of the dry hydrogen. So remember that the pressure due to the air, okay, because we forced the pressure inside and outside the tube to be the same, the pressure of the air is the pressure due to the hydrogen plus the pressure due to the water. So we want the pressure of the dry hydrogen, so the pressure of the hydrogen is equal to the pressure of the air minus the pressure of the water. Okay, so that's going to be 745 millimeters of mercury, okay, minus 18.6 millimeters of mercury. They're telling us all the numbers we need, and that answer comes out to be 726.4 millimeters of mercury. That's just a subtraction problem. Okay, so the last one, using the moles of hydrogen formed and the pressure of hydrogen, find the volume of this sample hydrogen. Using moles of hydrogen formed in A and the pressure of the dry hydrogen in B, find the volume of the sample occupies at 21 degrees. So what we're saying, we have moles, okay, we have moles in A, and we have pressure, find the volume. Okay, this sounds like a PV equals nRT problem. So we need to put, we want to find the volume, so V is going to be equal to nRT over P, okay, and I'm going to run out of time, so you just have to do this part yourself. So we know the volume, we want to find the volume, we want the moles, we know R And here's the answer.